Hi everyone, in this video we're going to talk about protein denaturation. In previous videos we talked about how when you take a polypeptide chain and put it into water, it will spontaneously fold, forming secondary and tertiary structures, ultimately giving a fully folded protein. I've drawn sort of a schematic view of a folded protein here. But if you could somehow unfold the protein, that process is called denaturing. It would then give back just primary structure, okay, which would just be the linear sequence of amino acids. This is sometimes referred to as random coil. Okay, basically just an uncoiled, unfolded protein. Now, if you were to somehow allow that to refold, that process going back to the folded protein is called renaturation. There are three primary ways that you could bring about protein denaturation. The first is to heat a protein. So by heating a protein, you're going to disrupt a number of different types of interactions. And let me just list those out here. So we'll make a little table here. So if I were to heat a protein, what are the sorts of intermolecular interactions that would be disrupted? So when you heat, you're going to disrupt hydrogen bonds and dispersion forces, or what we had referred to earlier as the hydrophobic effect. Heating essentially makes the atoms of the polypeptide start to vibrate much more quickly and will break apart hydrogen bonds. Now, when you often with a protein, after you've heated it, if you simply remove the heat, oftentimes proteins will fold back correctly. That's not always the case, but in some cases it is. Another way you could disrupt or denature a protein is to change the pH. When you change the pH, you're going to alter the protonation state of side chains, like the acidic side chains, carboxylic acids, like aspartic acid and glutamic acid. If you change the pH, you're going to change the neutral versus negative charge in those. Conversely, in changing the pH, you also affect the basic amino acids, histamine, arginine, and so forth. So those will change from being positive to neutral. And if you disrupt those salt bridges, or those ionic bridges, you could unfold a protein. So changing pH typically changes ionic bonds. It also can slightly affect hydrogen bonding ability as well, because it does change the polarity of the water solvent. But the main one it's going to do is to disrupt ionic bonds. Chemical denaturants can also be used, and these come in sort of two different flavors. You have the hydrogen bond disruptors. Okay, things like ethanol. Okay, another one that's often used is the molecule urea. What these are compounds that have the ability to form hydrogen bonds themselves. So if you were to have a sample of protein and introduce either, say, ethanol or maybe urea, what these will do is they will tend to slip into the folded parts and sort of compete with the hydrogen bonds that are in the folded part and essentially convert these into unfolded random coil. So those are hydrogen bond disruptors, alcohols or this compound urea. The other type of chemical reagent are the heavy metals. Okay, things like lead, mercury, silver. These heavy metals will often interact with disulfide bonds. So these often disrupt SS bonds. And they can also interact with carboxylic acids as well. And often they form covalent adducts to the protein that essentially take it from the folded state and force it to be in an unfolded state, or a completely denatured state. Now, that's the process of denaturation. If you wanted to renature a protein, many cases you can simply remove whatever the disrupting agent was. So if you were to remove the heat, you might then allow this to simply go back to the folded state. I'll give you an example where that doesn't happen. If you think of if you were to crack an egg open, the gelatinous liquid in the egg is composed of albumin protein. And as I'm sure you're all aware, if you take an egg and put it on a hot surface, like a frying pan, that egg will then cook, and the clear gelatinous protein, the albumin, will then denature and form a white substance, that's the sort of egg white, that's now a very different material. It's sort of hard and sort of spongy. And if you were to simply remove the heat, it's not as if the egg white then goes back to the clear, runny albumin. The reason for that is that once it's become denatured, it turns out that egg whites or albumin have a lot of sulfhydryl groups. And when you unfold the protein using heat, say for an egg white, you then allow multiple chains to then become unfolded, and then you often get cross-linking between different protein chains. So the sulfhydryl group that might have formed a cysteine within its own strand now could form a disulfide bond to another strand, and that's why you get this sort of cross-linked, irreversible protein denaturation. But there are many, many cases where simply removing the denaturant, whether it's heat or changing the pH back to its normal state, or removing one of these chemical denaturants, you can actually get a protein to go back from its unfolded state back to its folded. All right, so that sort of wraps up our brief discussion of protein denaturation.